Welcome to lecture 21, where we solve mixed problems on limits. Now, one technique that is very useful in many cases is the use of the absolute values in limits. Now, this technique is based on the following statements. If an is a sequence that tends to 0, then this is true if and only if an in absolute value tends to 0. Now, a similar statement is true for a function f of x. Let's say that limit of f of x as x goes to x0 is equal to 0. Well, this is true if and only if the limit of f of x in absolute value as x goes to x0 is equal to 0. Now, proving this is quite easy, and we'll provide the proof for the sequence because the proof for the function is totally similar to this. Now, let's prove the sufficient condition. Let's suppose that an is a sequence that tends to 0. Well, but that implies that for every epsilon larger than 0, there exists an n0 into the natural numbers, such that for every n larger than or equal n0, we have that an minus 0 in absolute value is less than or equal to epsilon. But this is just like saying that an in absolute value is less than or equal to epsilon, right? But we want to show now that this is exactly the same as saying that the absolute value of an, so this new sequence, which is the one generated by taking the absolute value of every element of the original sequence an. So what that implies? Well, if this tends to 0, that means that for every epsilon larger than 0, there exists an n0 into the natural numbers, such that for every n larger than or equal to n0, it happens that the absolute value of the sequence, but the sequence is just an minus 0, is less than or equal to epsilon. But we clearly see that this is nothing else than the absolute value of the absolute value of an, which is nothing else than the absolute value of an less than or equal to epsilon. So this basically shows that the two statements are totally equivalent, and a similar proof can be given for the limit of a function. Right, so let's see how to apply this, technique. And let's consider the example 1, where we have the limit as x goes to 0 of this fraction. We have a logarithm of the cosine of x divided by the arc tangent of x times the cosine of 1 over x to the cube. Right? So we immediately recognize that this is an undeterminate form because, well, this part of the function, let me call this function g of x. G of x has logarithm of cosine of x. When x goes to 0, cosine tends to 1, so we have 0 on top, and of course we have 0 below. So we have 0 over 0, which is an undetermined form. At the same time, cosine of 1 over x to the cube, we just proved that has no limit. So clearly this is something that we cannot establish by just replacing x equals 0 into the function itself. So we need to devise some other way of computing the limit. Now, the first observation, we observe that clearly cosine of 1 over x to the cube is bounded between -1 and 1. So if at some point we need to write an inequality, it will be easy to just remove cosine of 1 over x to the cube. So let's focus now, after doing this observation, let's focus on g of x. So we have that g of x is equal to the logarithm of the cosine of x divided by arc tangent of x. And we know that this is gives the undeterminate form 0 over 0. But we can rewrite this as follows. We can rewrite the logarithm, instead of writing cosine of x, we just use one of the tricks that we have introduced in previous lectures, and we know that this can be written as 1 plus cosine of x minus 1. And if we now divide by cosine of x minus 1 and multiply by cosine of x minus 1, well, clearly we have this first term that for x that goes to 0 will tend to 1. Okay, so we have already something that we know. And from the second term, we also see that if we divide by x squared, right, and we multiply by x and then again x, we have another term here, and we know that this will converge to minus 1 over 2. Now remember that we still have arctangent of x, and now if we divide by arctangent of x here, we have another known fundamental limit, because we know that this will tend to 1, and finally this will tend to 0. So we can easily conclude that this g of x will tend to 0. Now, using this result to evaluate the given limit is very difficult, because the entire function f of x is the product of a function g of x that tends to 0 times a function cosine of 1 over x to the cube that has no limit. So it would be impossible to establish what is the limit. But if we now apply the absolute value, we can get a useful result. In fact, we can write that the absolute value of f of x, of course this is larger than or equal to 0, and it is less than or equal of the absolute value of the logarithm of cosine of x divided by arc tangent of x. And we know that this, we just proved that this tends to 0, this is a constant, tends to 0, and by the squeeze theorem we know now that the absolute value of f of x tends to 0, which implies that f of x tends to 0 by just using the previous statement, and in particular the fact that we are using this part of the arrow. Knowing that the absolute value tends to 0, we can conclude that f of x tends to 0. So this is an example of use of the absolute value. Let's do a little bit of modification to the example. Let's consider this example 2, where we have So let's consider once again limit as x goes to 0 of the logarithm of cosine of x. And now instead of having we had arctangent of x, right? So we would like to replace this with arctangent squared of x. Let's see what happens. Arctangent square of x, all multiplied by the cosine of 1 over x to the cube. Once again, we have an undeterminate form because we have 0 over 0 times something that has no limit. Now, what is the idea? Why did I put a square here? Because I'm expecting when evaluating g of x, when evaluating basically this part of the limits, remember that this is for me g of x, I would expect a decomposition like the one that we have just considered, okay? Instead of having arctangent of x, I'm expecting arctangent square of x, so it is likely that this will end up in another limit that will go to 1, okay? So if we do this, in fact, let's repeat the process for g of x. We can rewrite g of x as logarithm of 1 plus cosine of x minus 1 divided by cosine of x minus 1, then multiplied by cosine of x minus 1, and then again we divide by x squared, and now we can just multiply by x squared divided by the arctangent square of x, and we see that this limit tends to 1. These limits tend to minus 1 over 2, and this tends to 1. So we can conclude that g of x is now converging to minus 1 over 2. Okay? So we can now get an intuition about what is happening, because if we have this element g of x, this part of the limit that's this part of the limit that will tend to minus 1 over 2, and this part of the limit that will be oscillating between minus 1 and 1, I would expect that this limit does not exist. So I want to prove that this limit does not exist. So this is the intuition that I get, okay, because I'm expecting a function that will be oscillating between minus 1 over 2 and plus 1 over 2. Now, if let's see if we are right in this intuition, and let's see if we can find, so let's find two subsequences an and bn such that, well, we should have an that tends to 0 with the f of an that will tend to a limit L1 into the extended real line, another sequence Bn that tends to 0 such that f of Bn will tend to L2 in the extended real line, and then finally we need to see that L1 is different from L2. Okay, so that's the idea. Now, well, that the idea is that because we know that g of x will tend to minus 1 over 2, we could identify an such that cosine of 1 over an to the cube will be equal to 1. Okay, and this means that 1 over an to the cube, where is the cosine equal to 1? When we know that this happens for the angles 2 pi n, which implies that an will be the cube root of 1 divided by 2 pi n. And we see that this sequence converges to 0, so the first condition is satisfied. And we also see that in this case, clearly f evaluated at an will converge to what? Well, it will converge to minus 1 over 2, right? Because basically the first part, this first part will converge to minus 1 over 2. This second part will converge to 1, so the product is just minus 1 over 2, right? Now let's find another sequence, Bn, where the cosine of 1 over b n to the cube is equal to minus 1, okay? So that implies that 1 over bn to the cube is equal, no, when is the cosine equal to minus 1? Well, when the argument of the cosine is 2n plus 1 times pi. Okay, just let me explain this idea very quickly. So we are saying this, if we have the unit circle, the cosine is gonna be equal to minus 1 in these points, okay? But these points are what? Well, we have pi, then we have pi plus 2 pi, then we have pi plus 4 pi, and so on and so forth. So basically we have pi, 3 pi, 5 pi, which are all odd coefficients. So we can say that this is just 2n plus 1 times pi. Okay, so this implies that bn will be the cube root of 1 divided by 2n plus 1 pi. Okay, and once again this will converge to 0, but then f of an will tend to 1 over 2. So we have, this is f of bn. So this implies that this is just a reductio ad absurdum. So this proves that the original function has no limit. Okay, so let's make a new step, and let's move to a new technique for solving limits. So, and this technique is about rationalization. This technique is useful when solving limits that contain roots. For example, let's consider the limit as x goes to plus infinity of x times the square root of x squared plus 5 minus the square root of x squared plus 7. Now, this is an undetermined form because we have the first x provide plus infinity, and the second parenthesis it will tend to infinity minus infinity. So this is clearly something that it is undeterminate, and the undetermination comes from the difference of the two roots. So we would like to remove this difference of the two roots. And if we just rewrite in general, so this is now a general consideration, if we have the square root of a minus the square root of b, and we want to rationalize this, well, we can just rewrite this as the square root of a minus the square root of b times a fraction, and we'll put square root of a plus square root of b divided by square root of a plus square root of b. But now we can multiply the numerators, and what we get is basically taking, this is just the product of a sum by difference. So what we get, a minus b divided by the square root of a plus the square root of b. So we have rationalized the initial difference of square roots, because we have now a fraction where basically on the numerator we have no roots, and this is what we are going to do now. So we can rewrite the x times square root of x squared plus 5 minus square root of x squared plus 7 by just applying the same method, with a being x squared plus 5 and b equal to x squared plus 7. Well, what we get at this point is just x times, we have x squared plus 5 minus x squared minus 7, and then we have the square root of x squared plus 5 plus the square root of x squared plus 7. And we immediately see that at the numerator, x squared and minus x squared, they cancel each other out, and then we're left with we can rewrite this as follows. Okay, we have x here, we have 5 minus 7 is minus 2, and then we can factor within the parentheses x squared. So we have square root of x squared times 1 plus 5 over x squared plus square root of x squared times 1 plus 7 over x squared. And again, we recognize that we have x minus 2, and then we have x squared, of course, is something that we can factor out from each parenthesis, and we are just left with 1 plus 5 over x squared plus square root of 1 plus 7 over x squared. But clearly for x that goes to infinity, we immediately see that this will tend to 1, this will tend to 1, these two will cancel out, and that implies that this limit is equal to minus 1, because in the limit we have minus 2 divided by 2. Okay, so let's give another example of rationalization. So example 4. Let's consider the limit as x goes to 0 of this fraction. We have another square root of 4 plus 7x minus 2, and then we have the logarithm of 1 plus sine of x. And once again we recognize that we have an undetermined form, because at the numerator we have 2 minus 2, so we have a 0. At the denominator, for x that goes to 0, we have another 0. So the problem is, once again, how can we get rid of the square root? Well, what we can do is basically rewriting the function square root of 4 plus 7x minus 2 divided by the logarithm of 1 plus sine of x. Well, we can multiply and divide by the square root of 4 plus 7x minus 2 or plus 2 and square root of 4 plus 7x plus 2. Okay, and now multiplying the two numerators, we have 4 plus 7x minus 4. And of course, we can immediately get rid of the 4 here. And instead, at the denominator, we have logarithm of 1 plus sine of x. And then we have 1 over the square root of 4 plus 7x plus 2. Okay, so now we can recognize sine of x as a function that goes to 0. So one possibility would be just to have, in the first fraction, we can leave logarithm of 1 plus sine of x, and then we can add a sine of x, multiply and divide by sine of x. So this way we have just considered this first element. Okay, but now we have also this element x here, and we can rewrite this x in this position. And then we have the fraction which is 7 divided by what? The square root of 4 plus 7x plus 2. Okay, and we are now in a position that we can evaluate this limit, because these limits for x that goes to 0, this will tend to 1. This will tend to 1, and instead this limit, well, this is a continuous function, so this can easily recognized as something that goes to 7 divided by 4. So the entire function has a limit in 7 divided by 4. Another example of rationalization is offered by this limit. Let's consider the example 5. And let's consider the limit as x goes to plus infinity of the cube root of x to the cube plus 2x squared plus 1 minus x. Okay, so what is the undetermined form here? Well, we have that the term on the left, which is the cube root, will tend to plus infinity, while the second term is minus infinity, so we have infinity minus infinity. So once again, we need to do something to solve the limit. And because we have a root, we may think to get rid of the root, but now we have a cube root. So we can use another type of rationalization, which is the following. Cube root of a minus cube root of b. We can now multiply and divide by the cube root of a to the square plus the cube root of a times b plus the cube root of b squared. And we need to divide, of course, by the same polynomial. So cube root of ab plus cube root of b squared. Now, why is this working? Because remember that, just a little bit of reminder here, if we have the difference of two cubes, okay, a cube minus b cube. We know that this, by elementary math, we know that this can be written as a to the square plus ab plus b squared times a minus b. So in our situation, a and b are square root of a minus square root of b. Okay, and of course, if you take cube root of b and cubed root of a. Okay, now if you take a to the square, what you get is the cube root of a to the square, and if you do the multiplication, you get the cube root of ab plus the cube root of b to the square. And finally, what you get is exactly a minus b. So that's the idea. Okay, by just replacing a and b with the cubed root of a and the cubed root of b, we get exactly this expression. So if we carry out the multiplication now, we see that we can get rid of the cubed root at the numerator, because finally we get a minus b divided by the same denominator, cube root a squared plus cube root of a b plus cube root of b squared. Now let's apply this technique to the given limit. So if we do this, we have that the cube root of x to the cube plus 2x squared plus 1 minus x, well, this becomes a fraction where we have x to the cube plus 2x squared plus 1 minus x to the cube, and at the denominator we have the cube root of x to the cube plus 2x to the square plus 1 all raised to the square, plus, well, then we have x times the cube root of x to the cube plus 2x to the square plus 1, and finally we have plus x to the square. Right? Now we immediately see that at the numerator the 2x to the cube cancel out. Okay? And if we just look at the denominator, well, clearly we have, in the first term, we have the cubed root of, I'm referring to this term here, right? So we have the cube root of this square, okay? So this is almost equal. We can say that this is basically equal to what? X to the square, because we have the leading term under the root is x to the 6. X to the 6 divided by 3 is x to the square. The same story goes for the second term, because the leading term under the root is x to the cube, which divided by 3 is giving another x, so we have another x squared plus x squared. So we can easily conclude now that the limit of this function, is basically 2 to the x squared plus 1 divided by 3x to the square. But because 1, of course, can be neglected when x goes to plus infinity, we can get rid of this, and we can easily say that, so I will just replace this with this symbol, which is approximated to that, and we can conclude that this limit is indeed 2 divided by 3. Okay? Now, let's apply the same technique to a slightly different limit. Okay, so this is the example 6. Another limit where we have roots and we want to get rid of these roots. Okay, so we have limit as n goes to infinity. Now we have a limit of a sequence, and we have the square root now. So this is the difference, that we have now a combination of a square root and a cube root. We have 2 to the n squared plus 3, and then we have a cube root of 2n plus 1, all divided by n plus 4. Okay, so what is the undetermined form of these limits? Well, clearly we have on top what we can approximate this with basically n square root of 2, right? Because the leading term is 2 to the n squared. We can extract from the root n squared, which becomes n. And on the other term, we have a term cubed root of 2n plus 1, which is negligible to that. So we can definitely say that this is infinity over infinity, so another undetermined form, right? Okay, so how can we solve this? Once again, we can make an approximation, and we can say the following. So we can say the following. We can say that this fraction can be, if we just keep when n goes to infinity, only the leading terms. At the denominator we have just n. Okay, at the numerator we have n square root of 2, right? And we have basically cube root of 2n. But because this goes to plus infinity slower, okay, we can say that this limit in the end is exactly square root of 2. Okay, so this is just one way of approaching the computation of limit by just looking at what are the leading terms, and we will make all this more precise when introducing the infinitesimal, or the infinite terms, but for the time being it's good to have just some practice with this technique. Now the next topic that we want to cover is what can we do when we have the limits for x that goes to x naught, with x naught different from 0 or x naught different from plus or minus infinity. Because if you realize, what we have done so far is always evaluating limits for x that goes to 0 or plus or minus infinity. And what if instead we have a limit in undetermined form where x goes to x0? So the fundamental idea here, so the hint is the following. Try to transform the limit into one limit for x goes to 0 or x that goes to plus or minus infinity. So we want to try to do this, and we'll see that this is very easy. For example, consider example 7. Consider this limit as x goes to pi of this fraction, sine of x divided by x minus pi. Now, what is the undetermined form here? Well, we know that if x goes to pi, sine of x tends to 0. but also the denominator tends to 0. So we have 0 over 0, right? So what we can do now is basically we can set x minus pi equal to a new variable y. So that implies that when x tends to pi, we have a variable y that goes to 0, and that was the idea, right? So the idea, remember, is exactly this. If we have that x goes to x0, and in this case x goes to pi, we need to transform this into a limit where with a new variable that tends to 0. And this is what we have done. We have set y equal to x minus pi, so that when x goes to pi, y tends to 0. Now, we can also, from this, we can also re-express x as pi plus y. So our limit now is limit as y tends to 0 of, well, sine of x becomes sine of pi plus y and divided by y. Okay, but this is just by using a little bit of trigonometry. We know that this is minus sine of y divided by y. And this is one of fundamental limits, so we know that this is equal to minus 1. Okay, so after the change of variable, it was quite easy. A similar limit is the following, where we have example 8. Consider the limit as x goes to 1 of logarithm of x divided by x squared plus x minus 2. Okay, and this limit is again 0 over 0. Okay, so we cannot just replace it. This is a continuous function, but we cannot replace x equal 1. Now, what we can do is basically setting. Remember that we need to have now a new variable that tends to 0. So we can set y equal to x minus 1. And in fact, when x tends to 1, y tends to 0. So this seems to be the right variable. And of course, x is now just equal to y plus 1. Let's see what we get now. So this becomes the limit as y tends to 0 of the logarithm. Instead of x, we'll put 1 plus y. And then we have what? Well, we have x squared, which is y plus 1 squared, plus x, so plus y plus 1 minus 2. Okay, so this is again limit as y goes to 0 of logarithm of 1 plus y, and we can rewrite this as y squared plus 2y plus 1 plus y minus 1. So we have 1 and minus 1 that go away. So we are led now to the following limit. So we have limit as y goes to 0 of the logarithm of 1 plus y divided by y squared plus 3y. And by just using one of the regular tricks, we see that these can be immediately rewritten as logarithm of 1 plus y. If we factor out 1y, we have just y here, and we have 1. Let's give a final example of limit with the square root. Example 9. We have limit as x goes to minus infinity of the square root of x squared plus x plus 3 plus x. Now, this limit is of the type infinity minus infinity. Now, we can possibly resort to one of the rationalization that we have introduced before, but it seems that the problem is due to the fact that x goes to minus infinity. So let's attempt a change of variable. Let's set y equal to minus x. Well, this implies that when x goes to minus infinity, y goes to plus infinity. Okay? So, and of course that also implies that x is equal to minus y. Now, this limit becomes limit as y tends to plus infinity of the square root. Well, x squared, of course, is y squared. X is minus y plus 3. And then we have minus y. Okay? And now we can do the rationalization. So we can rationalize this because this is exactly one of the examples that we gave before. So we know that this is limit as y tends to plus infinity, okay, of, well, at the numerator we have y squared minus y plus 3, and then we have minus y squared. At the denominator we have square root of y squared minus y plus 3, okay, plus y. And we see that now y squared and minus y squared cancel out. So this is just equal to the limit as y tends to plus infinity of 3 minus y, and we have the square root of y squared minus y plus 3 plus y. So you see that once again we can do an approximation here, because when y goes to plus infinity, of course 3 can be just neglected. So it is just like having minus y here, and the leading terms on the root is y squared, so this becomes basically 2y. So this implies that this will tend to minus 1 over 2. The last topic we want to consider in this lecture is how to evaluate the limits of sums. So let me give you an example of this and let me explain why this is worth considering. Let's consider the limit as n goes to infinity, right, of this specific sequence, a sequence which is expressed in terms of a sum of 1 over k squared for k that goes from n to 4 times n, right? So this is just one way of expressing a sequence an. A sequence an can be expressed just as the sum of a number of terms of the type 1 over k squared. Let's write down some of these terms. So this is the limit as n goes to infinity. If I start with k equal n, the first term is going to be 1 over n squared. The second term will be 1 over n plus 1 to the square dot 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 up to 1 over 4n to the square. Okay, so this is the expression. If we expand the sum, we get this. Now, one way of solving this could be saying, okay, for n that goes to infinity, the first term will go to 0, the second term will go to 0, and the last term will go to 0. So then we can say that this limit is equal to 0. No, this is totally wrong. This is not the way of doing this. And the reason is that the limit of the sum is the sum of the limits only if the number of terms that we are adding is fixed. In our example, the number of terms grows with n. So what I'm saying is that we cannot just consider this limit, we cannot just consider this limit as just the sum of the limits of each and every term, just because this number of terms that we are considering, let's see how many terms do we have here. How many terms do we have? Well, if I consider all these terms, this will be 4n, this is the last term. I need to subtract n, but then I need to add 1. So this number of terms is going to be 3n plus 1. So that means that the number of terms that we are adding grows with n. So when n goes to infinity, this number of terms becomes infinite. So we cannot just apply that the limit of a sum is the sum of the limit. So we need to be careful with that. I'll show you now how to find this limit. So what we can do is actually, let me copy this limit once again here. So we are dealing with this, right? So we want to find this limit. And now, and this is our an. And we saw that this limit, let me rewrite, this is the limit as n goes to infinity of, well, the first term is 1 over n squared, then we have 1 over n plus 1 to the square plus dot 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 1 over 4n to the square. And we saw that we have 3n plus 1 terms. So what we can say is that for this sequence an, well, this sequence is made of all positive terms, so certainly this is larger than or equal to 0. Okay, every element of the sequence is larger than or equal to 0. But at the same time, this will be less than or equal of 3n plus 1 times the largest of the terms that we are adding, which is 1 over n to the square. And now we see that because this term for n that goes to infinity, this of course will go to 0, right? Because we have n squared at the denominator and we have an n term at the numerator. So this will go to 0. This is a constant, will go to 0. And by the squeeze theorem, we can conclude that an goes to 0. So this is the proper way of solving the limit of a sum. Okay. Let me give you another example of a similar limit. So this will be example 11. Okay. So limit as n goes to infinity of this, we have 1 over the square root of n plus 1 over the square root of n plus 1 plus dot 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 1 over the square root of 4n. So once again, so in this case, an is exactly this. This is an, and we have once again 3n plus 1 terms for the same reason. Okay, and we want to see what is this limit. Now, we can say that by using similar considerations, we can say that an, of course, this is now a sum of terms with the number of terms that also grows to infinity. But we can now attempt to find another sequence which is basically pushing this to plus infinity, right? And what we can say that an is larger than or equal of 3n plus 1, which is the number of terms, times the term which is the smaller, right? And what is the smaller term? Is 1 over square root of 4n. But we clearly see in this case that this term, which is on the left of the inequality, will diverge to plus infinity. Why is that? Because we see at the numerator a term with degree 1, at the denominator a term with degree 1/2, so clearly the power wins at the numerator, so this will diverge to plus infinity, and this will push, by the squeeze theorem, an to diverge as well to plus infinity. Okay, so this is another example, and let me conclude with the final example, interesting one. This is example 12. Let's consider now, more in general, a limit as n goes to infinity of 1 over n to the a plus 1 over n plus 1 to the a plus 1 over 4n to the a. And you recognize that this is just a more general example of the first sequence that we have considered. Okay, in the first sequence we had a equal to 2. Now I want to see what happens for every possible a, and what I'm gonna say now is the following, is that for a larger than 1, so this will go to 0 if a is larger than 1. How can I get this intuition? Because I know from the first example, right, that we had a equal 2, so that was the exponent of every fraction, and we just proved in that case that the sequence tends to 0. So yes, it makes sense that I will generalize this result, because that implies that basically at the denominator here I will get an exponent which will be always larger than the 1 at the numerator. So I can definitely conclude that if for every possible a larger than 1, the sequence will converge to 0. The same way I can ask what happens if a is less than 1, which is pretty much the same example of this other sequence, where I see that in this case the exponent of each and every term is 1/2, which is less than 1, and with that same consideration I can conclude that there will be, the sequence will diverge to plus infinity. So the only thing that remains to be considered is what happens for a equal 1. But let's see something. For a equal 1, an, remember that this is my sequence an is bounded. We can prove that this is bounded by positive constants. Let me prove this, okay? So I have an here. I would like to find a sequence which is larger and a sequence which is smaller, okay? How can I find a sequence which is larger? We still know that the number of terms is 3n plus 1 and 3n plus 1. Now what I need to do basically is writing something, a fraction here, which is the smallest of all possible numbers,